Is the screen visible?
Yes, sir.
Okay, good. So far, our encounter in machine learning was primarily with respect to what is called as supervised learning, right? Because in the premise was such that we will be given as input as well as the output, and this is what is given to us in terms of training. So we know the level of the data attributes that we have, right? So this is what we till now did in supervised learning setup. Now, in many situations that you always do not have such kind of data in your hand, that is, you will not get the set of training data where you will be given as well as the output, but sometimes you need to cluster the data and detect certain anomalies or frauds, or maybe detect certain clusters and report it as depending on their cohesions. For example, you may think of this as that, let's say I have two attributes, x1 and x2. So this is x1 and this is x2. And instead of I am having plus or minus or some levels, let us say I'm given the data like this. You are given certain attribute value points and everything is in orange. So you can see that there is no such level given here. So one of the applications you may easily think that, let's say there are certain attributes of viruses as you have seen in your project. Now I have to detect which of them are classified as coronavirus. So maybe certain attribute matches, x1 matches for this one as well as x1 matches for this one, but they are different in x2 attribute. So depending on that, I need to make a class or a cluster of such kind of data sets that are given to me. The other thing you may also notice in this kind of problem is that there may be something which is far away from what is given, which means that there may be something which we call as anomaly or fraud. Let's say these are the credit card approval kind of a data set where there is someone here. It may be a fraudulent data. So noise, frauds or anomalies, extreme weather, you may take another examples, are all these cases where not only the clustering matters, but also something is there outside the cluster will act as an anomaly and you need to report that sometime also. So whatever we are discussing is in the realms of from supervised learning, or we are going to unsupervised learning. And as you can see, the term unsupervised means that there is no supervision as this, because earlier the teacher told you that what will be the level while training with respect to the input. Here you are only giving training data and you do not know what is the level of it. You are given such kind of a data set and this is your training examples. Now this setup we also called solving this thing, we also called this as clustering in data mining terms, because ultimately what we need is to group these data sets together and try to find out clusters from there from those data sets so that it separates out. So that is the overall goal that we want to do, that we want to cluster these data sets. So immediately you can go on thinking that while we cluster this, what are the features that we are trying to look? We are trying to look for similarities between the data, isn't it? We are trying to look for similarity. Similarity meaning the closeness will dictate the similarities, and the farthest the point, the more dissimilar would be the point. The farthest the points, the more dissimilar would be the points. So when we say that we have done a set of points into a cluster, so depending on the similarity, what is our goal would be in clustering is twofold. One, we need to minimize in intra cluster distances, that is the distances within the clusters, and we need to maximize inter-cluster distances. That means the distance which are between two clusters, we need to maximize as much as we can. So that is what our goal in clustering would be. Now, you can see I have already introduced certain kind of English terms which we need to define. That similarity, what does similarity means between points? What does this distance means between clusters? So all these things we need to define as we go along and determine our clustering algorithms. So here the overall goal is based on the similarity. We'll group a set of data points together and it will form a cluster with the goal that intra-cluster distances between the points will be minimized and inter-cluster distances between the points will be maximized. So let us say when we say similarity, distances, all these things, so obviously distance is an important attribute that we need to define first. So first let us try to define what does we mean by the distance between points. So let me give you some examples to think around this line to come across a distance. For example, if I say I give you a string like apple and I give you another string like appy. So if I say what will be the distance between these two strings, and having the programming knowledge, you can easily do one way that it could be the difference between the letter positions in each of these, and then I sum up with all the differences, right? That could be one measure of the distance. So here, for particularly this string examples, the distance is the sum of the distance between letters. And obviously, as you can see, if we say this is the metric that I define as distance, then obviously I can define similarity is proportional to the inverse of the distance. The more the distance, the less they are similar, right? So this is one kind of example through which we can figure out that given 2 points with different attributes, suppose this is attribute x1, this is x2, this is x3, this is x4, this is x5, I can compute distance by certain distance measure. However, in all these cases, when we try to compute distance, usually three things or three mathematical notions should be obeyed. One is called as symmetry, which means the distance between 2 points A and B is same as the distance between the point B to A. It means if there are 2 points A and B, you measure the distance this way or you measure the distance this way, both will be same. The second point that you need to consider when you design such kind of a distance matrix is also reflexivity, which means that the distance of a point with itself is 0. And the third one, which we need, is triangular inequality, which says that if I have 3 points A, B, C, the distance between A to B plus B to C will always be more than the distance between A to C. So the distance between A to B plus the distance between B to C will always be more than equal to distance between A to C. And you can easily see when it will be equal, if they are collinear, right? So when you design your distance matrix, you need to follow these three particular principles, whatever distance matrix you design for your problem. As you can see here, the distance, the similarities and all also followed this because reflexivity is obeyed. A to B and B to A will be the same if we take the absolute values. Triangle inequality is, it will just be equal for all these cases because we are just adding up to find in the alphabet series. So this is the first consideration, that we need to find out a distance or similarity matrix by inversely having a formula inversely proportional to it, and whatever be the distance between the points should follow these three principles. Okay, so based on this understanding of the problem and the initial notion of distance in our head, let us try to figure out certain algorithms to solve the clustering problems. Any questions till this point?
No, sir.
Okay. So now the question is that let me draw up a clustering example, then it will be easy to illustrate. So here I have certain points like this. Here I have certain points like this. Maybe I have certain points like this, and it may be the case, though I have drawn two clusters which are of good shape, it may be the case some cluster would be like this shape. So this is x1 and this is x2 attribute. So at the end, when we by our algorithm with these data points having our distance matrix, we come up with such kind of a cluster. So at least later we will see more ramifications on this, but at least we need to see one evaluation matrix of this, that how do we know that a good clusters we have formed. So one evaluation technique we use is called scatter coefficient. The concept is very simple. That's why I introduced it in the beginning, that after our goal has been achieved, we will evaluate how good or bad it is. So scatter coefficient, I'm abbreviating it in SC, is nothing but it is the average intra-cluster distance divided by the average inter-cluster distance. What does it mean? It means, see, intra-cluster distance means from a point, the distance within its cluster. So if I take from every point to all other points, all the distances, and sum them up, and then take an average with respect to the number of points, that is the average intra-cluster point distances. So for this cluster also, suppose this is C1, this is C2, this is C3. So we will do all of this and take the average over the number of clusters as well. And then we will also try to see that what is the inter-cluster distances from every point. And then for each of the cluster, we will try to build the average, and for all the cluster, again taking an average, right? So what do you think, that if it is less, it is good, or if it is more, it is good?
Less.
Less is good.
Yes, because our principle was to minimize intra-cluster and maximize the the intermediate among the cluster distances. So the numerator we are trying to minimize, and the denominator we are trying to maximize by a good clustering algorithm. So obviously we would be happy if we get this. This is not desirable, right? So we will try to see
Sir,
that what if, yeah.
sir, can you repeat how we will calculate average intercluster distance?
See, inter or intra, the denominator or the numerator?
Denominator.
Denominator, for every point to every other cluster points, you take a sum. Okay, you go on doing this for the other points as well. Take an average among the points of all these sums with respect to the points that you have. That is your average intercluster distances.
So that will be computationally inefficient. So can we do it like this? Like for cluster C2, we will find the centermost point,
Centroid.
like the
Wait.
centroid.
I'm coming. I'm
Yes,
not
sir.
saying it is computationally good or bad. I'm saying this is a measure that people use. Computation I have
Yes,
not
sir.
started yet. Okay. So by definition, scatter coefficient is this.
So why are we taking only 3 clusters?
Yeah, that also I will come. I mean, so you're absolutely, your questions are valid. That one of the questions come that computationally efficiency One of the other of the question is number of clusters, how many, right? This is your question.
Yeah.
So see, yeah, all these are valid questions, but I'm just reaching to a premises of answering these questions from the problem itself. So till now, I just declared a problem, and let's say I know the number of clusters. I declared what I need to solve and get into, and with while solving it, what will be my basic distance function, what it should obey. That three things I declared till now. These questions are still yet to be clear up. Okay, but see, your this question, at whatever knowledge we gathered till now, your these questions can have one answer, though it may not be acceptable answer, but I can say one answer, that you will consider, let's say, your number of clusters k equal to 3, k equal to 4, even k equal to 2. You will do that and compute the scatter coefficient, whichever is the best, right? You can take it, isn't it? Because scatter coefficient says what is the efficiency of the clustering in terms of, I mean, as you can see, it's a cluster cohesion versus separation, that how the clusters are internally I mean, how much cohesion they have internally vis-a-vis with respect to the separations they have. So
Sir,
if
if
you
we
have
take
bigger clusters, then the separation is totally bad, right?
no, if we take the number of clusters to be same as the number of data points, then SC would be 0.
Absolutely, SC would be 0, but that doesn't give you. I will tell you that to do that, your SC would be 0 because average intercluster you are reducing it to 0, but that will not solve your purpose. So
Yeah.
this is a term. Yeah, that will not solve your purpose. I will gradually go into the more detailed coefficient, I mean, evaluation things. But what I want to say that if there are, let's say, if there are points within a cluster more than one, let's say, one of the things that we want to do is to minimize the inter-cluster distance, rather intra-cluster distance, and maximize the within cluster distance. That's what we will try to achieve. Now, how many we will see later. Okay. So often, as you can see, that this is the term often experimentally people find out, and often it is just on experimental basis. We need to just stick to it. We cannot have a theoretical result that this is the best k in this partitioning, because it is dependent on how you interpret the data and what are your out of sample data, isn't it? Because if my out of sample data does contain some data inside this like this, then I would have merged these two clusters if I knew those beforehand, right? So that is the way that we need to see that it is how well we can cluster in sample, with the fact that through experiments how well we can get it. And one point, a cluster is out of the question, that we will not think at all, because when you are given a data set for unsupervised thing, you obviously mean there will be some link between your data points. You will try to figure out that, but k is a defined value that designers take and explore on a range. So what designer knows is a range of k, that my k will be less than 8 and it will be more than 3, but I exactly do not know. I know that there are 3 types of different viruses that samples I have. 3 to 8 types of different viruses are here in this particular zone of India. Now I am taking the samples and I need to classify how many types I can get.
So
Right?
the
That
range
is
is known.
range is usually it is from the domain knowledge. It is from the domain knowledge. It is supplied to you, but what you do not know is the exact value of k. That depends on how good you are trying to cluster, and you have to evaluate that way.
So, but still, how will the scatter coefficient help?
Meaning, I mean, the less is better.
Yeah, but if we like from 3 to 8, if we increase the number of clusters from 3 to 8, the scatter coefficient would definitely decrease. So
Why? It
because
also depends on the inter-cluster distances as well, and the
yeah,
intra-cluster distances.
so
So
if
wait. What I'm saying is that you let's say if my k is equal to 2, what does scatter coefficient say? Suppose I have this kind of a data. Now, is this type of clustering good? Scatter coefficient will say no. Rather than this type of clustering, scatter coefficient will say yes.
Oh,
Do
okay.
you get it?
Yeah. Guess yeah.
Yeah.
Sure.
But this navigating how many clusters is purely experimental. Okay. For that, people do not follow scatter coefficient. People follow something called Silhouette coefficient. I will come to that.
Okay.
Okay. But it says cohesion versus separation. That's only. So scatter coefficient is a measure between cohesion versus separation. So now, as you can see, it's obviously the set of clusters that you make is obviously a partition in the data points you have. And in mathematical sense, you can find it that the partition will induce an equivalence set between the set of points with respect to the distance as your function. So since we can view clustering as a partitioning, so there are two types of partitions we could possibly get. One, what we do as hierarchical clustering, and the other we call it as a partitional clustering. So hierarchical clustering, you can easily see, since the hierarchy name is involved, it is either you go from top down or you go from bottom up. And let me tell you the strategy, it is very easily understandable. Given a set of data points, so what you do is that suppose you are given a set of data points in your hand, you try to compute the distance between this pair of data points. So this pair of data points, you compute the distances, and the nearest one you merge. And merging means telling that these two forms one cluster. Then you need to again compute the distance considering this as one cluster, and these all are initial single point clusters. So we have defined distance between points. We are yet to define distance between clusters, because after one merging, 2 points came inside one cluster. So now, so we have defined distance between points A and B. We also have to define distance between clusters C1 and C2. So this is yet to be known, but this we have defined. So with that, let me first give the strategy, then how this distance will come, I will immediately point out. So with that, then again with this cluster, if I can find what is the minimum pair, then what I will do, I can merge it. Then suppose a minimum pair, I can find this. Then the minimum pair, I can find this. Then the minimum pair, I can find these two. Then the minimum pair, I can find these two. Maybe the final minimum, I can find these two. So what does it mean? At each step, what you are doing, at each step, you are trying to build a cluster at each step. See? And then between two clusters, when you are merging it here, it means that you are trying to merge. So these two cluster is merged first. So this cluster is being formed. Then again, when you go up, you are going to merge this and form this cluster. And when you go up at the top level, you try to merge all and form them in the same cluster. Now you can see, depending on the value of the number of cluster k, I will just cut the tree as I need up to k minus 1 depth. Agreed? If I need 3 clusters, so I need this kind of 3 headings. So I will cut it here. I will stop merging and moving up to this point. That will create 3 different clusters. So one clusters will be this, one clusters will be this, and the third clusters will be this. Agree? So two new things come up. Yes, questions? Two new things come up. As you can see, this is obviously bottom up clustering. And the second thing, we somehow drawn such kind of a tree like structure which is called as dendrograms in machine learning parlance. So this is a dendrogram, which is a tree like structure upside down. We call it as a dendrogram. And this bottom up clustering, as you are given in the project, is also called agglomerative clustering. Is also called agglomerative clustering technique. So we are in the realms of hierarchical clustering. As you can see, it's an hierarchy based finding the clusters. We will try to create the distances between the points is the first level, but distances between cluster we are yet to define. We will immediately define it. Once we can do that, then we will calculate the minimum distance among the clusters and group them and gradually move up to k minus 1 depth, because if I need k clusters, I need to cut this. If I move up fully towards the root, then I will get only one cluster because everything is merged. At each step, two clusters are merged and you move up. Here, two clusters are merged. Here, two clusters are merged. Here, two clusters are merged. Here, you move up, again merged. So you can see there are k minus 1 merging points you will find. So therefore, if you need k clusters, so you need to cut the tree in between, this dendrogram in between. And this is called bottom-up or agglomerative hierarchical clustering. And with that, you can easily see the flipped level of algorithm, which is the top-down. What you will do? Can you just guess what you will do? Suppose you have this setup.
We'll assume that everything just makes one cluster and then split it at every step.
Exactly. It's both are recursive, right? We will first assume this makes one cluster, which means that all your points will form one cluster. Then depending on the distances, you will try to split it. Let's say I first split it this way, or I split it this way, or I can split it this way. So depending on all possible splittings that are possible, that is one in one side, the other in the other side, and two in one side, the others in the other side. Depending on all these configurations, you figure out which gives you the best part of splitting, and you split. So the same tree we will result. However, you can see the same tree we will result from the top side rather. We go on splitting, 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 and finally reaching to the points which are only single points. So when you look from this angle, every point forms one cluster. When you look from this angle, from this position, the second level of position, you can see this is one cluster and this is one cluster. So therefore, when partitioning, you have to see all possible combinations which gives you the best cluster, and there the distance will again come into picture. So this is just, as we can see, that this is just the top-down method as opposed to bottom-up, and both are recursive. And we call this top-down method as also as divisive clustering. And you can easily find out why the name comes from, because it is dividing the total cluster into different classes, divisive clustering. So now with all this small little algorithmic jugglery, as you can yourself figure out, as I said, common sense, we now will define what is the distance between the clusters. So there are many metrics people usually follow, but the widely used follow is these three. One is the average distance. So the average distance your friend has already pointed out. Suppose I have two clusters. One is this. One is this. I will try to find out the centroid of those two clusters. and I will try to find out the distances between the centroid and take an average. So this is just the average of the centroids of cluster Ci. So this is your some cluster C1. This is some cluster C2. There could be many more such clusters. Each clusters you will compute a centroid and try to figure out what is the distance of the centroid with respect to each cluster. Take the sum of the distance and take an average with respect to the number of cluster pairs. That we say that the average distance, or if we have to only take distance between two clusters, is just the distance of the centroid. So since it is a centroid and we are only discussing about the distance between clusters, so the average doesn't matter. It's just the centroid distance between two clusters. So centroid forms the average within a cluster. Centroid's distance Ci to Cj. The second is what is called as the mean distance. So mean distance, you can easily see that two clusters, let's say C1 and C2, let this figure be non-cluttered. For C1 and C2, as you can see, let's say these 2 points. I will take the minimum among all pairs of points which lie from one cluster to the other distances and take the minimum among them. Okay, so distances between the closest point of two clusters. So it is the distance between closest of Ci and Cj. And you can easily guess what will be the last one. It will obviously be the max distance. Max distance, you can understand that the maximum distance between 2 points of a cluster. So this is the distance between farthest point of Ci and Cj. Now, you can see here we assumed the distance between points seamlessly because we have declared it, and for the strings I have declared it in my way, and that will satisfy the properties. And in your project, as you can see, there could be cosine similarity as your similarity index. The inverse will be the distance. You can also see Euclidean. You can use Manhattan distances. All those distances we already have seen in which algorithm? K nearest neighbor, right? We can see all those distances and can use them unless and until it follows the principle of those three rules: symmetry, reflexivity, and triangle inequality. So this is a distance between points we can take, and distance between clusters are this. And depending on which distance between cluster we follow, in agglomerative or divisive clustering, the name of the clustering algorithm changes. And if we follow average distance, the clustering algorithm is called average linkage clustering. If we follow this one, if we follow the second one, then it is called single linkage. Some of you are given the project like this, single linkage clustering. If it is single linkage agglomerative, it's a bottom up. Mean distance is the distance between clusters that has been followed. And the third one is some of you are also given the project with, is called the complete linkage clustering algorithm. Now you can see one thing, that why the name single comes from, because it's the minimum distance. So at least there is a single link within that distance that connects between these two. There is a single, if you allow that distance, that minimum distance, there will be at least a pair of points that is getting connected. So it is named as single. Why this is complete? Because you are allowing the maximum distance that can be possible between two data points that are given to you, which means that all other data point distances are less than that. So if I give you that the data point distance is maximum this, then all other data point distances falls inside this range. So it's a complete distance measure kind of a thing. So people give the name as complete linkage. But as you pointed out, the main drawback of this hierarchical, or I mean top down even and bottom up, is the computational complexity. Because you can see that here I need to compute every pair of points and then try to figure out a cluster, every cluster, and then try to figure out the next level of cluster. If you move up in this dendrogram, initially every pair of points which is closest, then cluster it again, every pair of such things which is closest. So at each step only one number of cluster reduces, or one number of point reduces at every step. So it is very time consuming. So you need to follow n minus 1 step to get into the overall dendrogram to act upon. Then you can cut up to this level of depth k minus 1 to get your desired answer. So at least you need to go all of these steps in the dendrogram to complete your clustering. And every point to every other point, you need to go on discovering the intercluster distances and all. However, and also there is a disadvantage. It is very sensitive to noise as well. So let me draw a diagram and show it what happens. So there is no point that this kind of algorithm is catering towards the noise or not, because every time you will see a point which are noises, maybe here and here. Even if you form a cluster, if the number of cluster is lesser than what is the desired cluster due to the noisy point, it will try to form a cluster with that noisy points also into picture, right? Because I keep on moving until I found my desired k number of clusters. So even if it may be the case that you form a clusters like this, right? So two drawbacks of all this clustering. One is computational, and one is noise in data. So these are demerits. Can you point out one merit of this? I have already drawn here. What is the merit of this algorithm? Can form arbitrary separate clusters, because it only needs the distances and trying to cluster it. It doesn't make sense to have. So even if I have clusters like this form and clusters like this form, it will easily identify the cohesions and can do it, because I am trying to see which are my nearest and trying to group together. So it can form arbitrarily shaped clusters is one of its advantage, but computational inefficiency is one of the major demerits. So to cater to this, people also thought about partitional clustering technique, which is very widely used, and the most widely used is called k-means algorithm. You might have heard the name k-means. The principle is very simple, though it is computationally very efficient. The principle is very simple. What I will do, depending on the k which is predefined, as your friend told us, you may explore with certain numbers, but it's predefined when you start this algorithm. Given a value of k, you try to keep k number of such buckets. I'll give an example immediately after saying the algorithm. So you have data points d1, d2, dn, and you have k buckets b1, b2, bk. Arbitrarily choose k points and put into this bucket. Any arbitrary k point you choose and put into this bucket. Then for every point d1 to dn, try to compute which of this point that you put inside it is nearer. So is d1 nearer here or with respect to this point or with respect to this point. So let us call this point as the pivot of B1, as the pivot point of B2, as the pivot point of B3. With respect to the pivot points in each bucket, I iterate over the data and try to figure out which of them are the closest, and accordingly I keep on pushing my data point in according buckets. Clear? Yes or no?
Yes, sir.
Yes, sir.
So therefore, then this bucket will contain several sets of points, may not be equal, but there will be several sets of points that I can figure out depending on the similarity or closeness in the distance. Take every bucket, try to compute the mean. That's why the name k-means comes from. Try to compute the mean or average of this point. Try to compute the mean and average of this point. Let this be m1, m2 up to mk initially. Then the mean becomes m1 dash, m2 dash, mk dash. See, initially it was not mean, it was arbitrarily 1 point. Then it was a mean. And you only keep the mean inside it, throw away these points. Just keep the mean, throw away these points. Remember that this mean could not be within the point itself, because D1 and D2's mean is average of D1 and D2 may not be inside this set as well. So this is a totally new point which is not in my data point set, right? So you keep this mean and throw away all the points D1 and D till Dn, and again do the same exercise, whether D1 is closer to here, D2 closer to here, D3 closer to maybe here, and go on. Dn is closer to here, and go on. Again, you compute the mean, m1 double dash, m2 double dash, m3 double dash, throw away the points. Continue this way. Okay? Until there is no change in the distribution between the previous and the current iteration. The points that you basketed in the previous time and the points that you basketed now are the same. Understood the algorithm?
Yes, sir.
Yes.
As you can see, what this mean will suggest, just let me give an example that will be the best. How does the mean changes and all? Let me figure out arbitrarily. Let me make it small so that we could understand it step by step. Suppose I have 6 points. Let's say one is here, one is here, one is here, and maybe another one is here, here, and here. So if I level the points, this is 0, 0 as per my x1 and x2 2 dimension. This is 1, 0. This is 0, 1. This is 2, 2. This is 2, 3. And this is 1, 3. Step 1. Initially arbitrarily pick up 2 points in 2 baskets. Suppose these are my baskets. So arbitrarily I can pick any point. So let me pick up these 2 points. I picked up this and I picked up this. Try to find the nearest among all the points that we have. So 0, 0 is nearest to itself, goes in here. 1, 0 is nearest to itself than 0, 1, because this distance is root over 2, this distance is 1. I am taking distance as Euclidean. I am taking Euclidean distance as my measure. So you can see that this point goes on. 1, 0 goes on here. Similarly, all other points, you can easily understand that all other points will go into this basket, right? Because all other points are closer here. This point, and this point are closer here, right? So this will be my final basket when I do with my 6 points. Step 2. This is initial step. Step 2, compute the mean. What is the mean of B1 and what is the mean of B2? Just the average. What is the mean of this? Anyone?
5/3.
By 3?
And
4. 4 points now. All points you have.
oh, acha. 5/4.
Right?
9 by
9/4.
Yeah. Now see
9
what
by 4.
happens.
9/4.
No, 3, 3, 6, 7, 8, 9 by 4. Sorry, it is then 2.25. Now see what happens. Essentially, at the initial iteration, you thought this one is your mean centroid. Now your centroid shifts here, right? 0.50 B1 basket, which means the points that you put inside it, it is trying to pull its centroid somewhere in the middle. Here also, when you say 1.25, it is somewhere 1.25 and 2.25. So 1.25 is here, 2.25 is here. So your centroid pulls out here, isn't it? So as if it is trying to form a centroid of a cluster between these four after the first iteration, right? Repeat the same algorithm. With respect to 0.50, what are my closest point? Now you can see with respect to this point in basket B1, my closest point are these three. Because I have this point here in basket B2 and these three are my closest. So obviously here 0, 0 will come in, 1, 0 will come in and 0, 1 will come in. And in this basket, 1, 3 will come in, 2, 3 will come in and 3, 2 will come in. Right? You do not have to consider this anymore. Again, compute the mean. Third step among these points. So what will be the mean in basket B1 and what will be the mean in basket B2?
0.33, 0.33.
0.33, 0.33, and in this basket, 6 by 3 is 2, 3, 3, 6 to 8, 3 is 2.66. So let us try to visualize. 0.33, 0.33 is somewhere 1/3 and 1/3 is somewhere here, right? And this centroid is 2, that means here, and 2.66 means, sorry, this is 1, 2, 2.66 somewhere here, right? 3, 5. No, this is 5 by 3. Sorry, this is 1.66. This I made a mistake. This is 1.66. 3. This is 2. That's why 1.66. So the point here is 1.66. That means around this line. This is the new centroid. Now what happens if I repeat it? But if I repeat it, see the number of points that come in here doesn't change, and the number of points that come in basket B2 also doesn't change. So I stop. So what does it indicate finally? This is kind of a centroid of the points you have, right? So this is your cluster. This is your cluster. This being the kind of a centroid of the average or the mean point. If you understand this, then two questions for you. I mean, not the questions, two things to try. Try with k equal to 3, 4, what happens? And the second question, initially, you see, at the initial step, we have arbitrary choice of points, right? We arbitrarily chosen 2 points. Since we randomly or arbitrarily choose, it is this algorithm experimentally performs very well because most of the times the arbitrary points often are the points from 2 different clusters. Try to understand this. Had I chosen 2 points from a 2 different clusters, suppose I chosen 1 point here and 1 point from this cluster arbitrarily, then what would happen? It would converge much easily because after first iteration, it knows what are its cluster points, right? So therefore, if the distribution is very generic or identically distributed, and if you take out just k number of points arbitrarily, there is a high chance, expected value wise, there is a high chance that you land up to different points from different clusters, which will make your number of iterations more efficiently and less. And in each iteration, you can see what you have to do. You have to go for this n number of points to compute the distance and then put it right, and have to compute the average between them. So computationally, it is not the case you go for NC2 number of pair distance computation every time when you cluster. In your merging, the top down or the bottom up merging, what you do? Initially, you have n points, you compute the distances between every pair of such things. Then after one cluster is being formed, the number of points reduces by 1. Then again n minus 1 C2 number of distances you compute. So if effectively you compute NC2 plus n minus 1 C2, right? This many distances. And it is obviously, you know, this is of the order of, isn't it? Yes or no?
Yes, sir.
Sorry, did I make a mistake? Will it be the order of 2 to the power n? What will be this thing evaluates to? This is not 2 to the power n. I made a mistake. Just correct me. Come on, you should tell this. I am making mistakes. What is the complexity here? Pairwise distance computation, n minus 1 reducing each time.
Approximately n cube.
Yes, it will be of the order of n cube. What is here? I leave it. I hope you got the algorithm. Just try to figure out the complexity in the worst case. In the worst case, you figure out all points belong to one cluster initially. That's the worst case. Okay. So experimentally, it has been shown due to the randomness in the initial part, the number of iterations, usually it takes very less. Obviously, it should depend on the number of iterations, your complexity, but usually it is very less. And you can see in each iteration, there is order of n number of operations going, because n points you need to just see whether it belongs to which basket, right? You need to just see that. Is it order of n? I purposefully made a mistake here. What is the time taken to convert each of the point into its appropriate basket? You are not thinking. You should immediately stop me that something is going wrong. See, there are k basket. Try to think in this way. There are k basket. A point has to be anywhere here, which is the nearest one. How do I get it?
K into n.
Naive algorithm is k into n. You are right. Naive is k into n. I have to compute each of the k for all the n points one by one and find which is the nearest. Right? Still better than order of n square, even if this iteration takes n number of times. Right? Because k is obviously much lesser. It's a constant much lesser than n. But try to think that whether any computational geometry, there is a many line sweep algorithms which does it very efficiently, maybe in the log n space, log n times of the order of k log n something. Just try to figure out to find out the closest pair of points and all that. All these algorithms helps. So I leave it to you this part, that what will be the complexity in the worst case. K into n is obviously an answer. Can you improve it? Just think of the algorithm, and there are many such improvements you can find also in any of the literature. So we are almost closing the time, but let me just
Sir,
give you one to, yeah.
there is a divide and conquer algorithm to
Yes,
find
yes,
closest pair of points.
yes.
Are you
That's why I
Yes,
said
sir.
login. Yes, absolutely. That's why I said that this is correct, but we can improve. We can
But
improve.
that will require sorting of the points.
Pre-sorting, correct, pre-sorting. But see, what the thing is that pre-sorting, if you once do it, here basketing is done at every step once, right?
Yeah, that will definitely help.
Yeah, so there will definitely be an advantage even if you pre-sort it once here. You are absolutely right. There is a pre-sorting step to get it in login. That is once, and then you can do it. But anyway, we are not. We are not eliminating the barrier of in login, so pre-sort will not hamper. Until and unless there is a k, which is a significant amount of k, we cannot reduce the barrier of n login anyway.
Okay.
So this is very fast. This algorithm is very fast. Unlike the previous one, which is sensitive to noise, this one is noise robust because you can see there is a pull of the set of points to form a cluster. As you can see here, though I started off with here, but there is a constant pull of a set of points which drags it into a cluster and releases this point to form inside this cluster. Are you getting me what the point that I am telling? Though I thought about this may be forming a separate cluster than this one initially, there is a constant pull of the second cluster towards its set of maximum point densities, relinquishing this point from that cluster, making it so this feature particularly of k-means makes k-means algorithm robust to noise, because if there is an outlier, even if that point I pick up initially, there is a chance that I will relinquish and come back here and form my cluster. You take an example, two examples. One, with this example, try to see what happens with k3 and 4. Take an example where still I have a point, for example, 10, 10. Some points I have 10, 10s. What happens if I pick up that? And what happens if I do not pick up that? If I do not pick up that, obviously what will happen? If the two clusters would include 10, 10, we will have such kind of a thing. And then from the definition of the intra-cluster cohesion, I can figure out there is something wrong in this cluster, because the intra-cluster cohesion will get disturbed due to this outlier point. Immediately, I can find out, since there is something wrong in this cluster, if I stop earlier and make more number of clusters, only this point will stand out. So it's an outlier. So there are very many ramifications of this to detect fraudulent cases, extreme weathers, something that is an outlier and all this. So hence k-means algorithm is being widely used in many classes. Get it? Any questions in this? I will stop here, but if you do not have any questions, I can just.
Sir, can you please repeat the 10, 10 point part?
Yeah, I am saying that if there is so do you understand that k-means algorithm is robust to noise?
Obviously. Yes,
Obviously,
yes.
because it pulls it into the dense set of points. Now, if in this example I had a point 10 cross 10 and I give you two cluster to cluster, so what will happen at the end? It will happen that you have these 3 points, one cluster, but 10, 10 will be on the top cluster, because I gave you two clusters to cluster all of them. Obviously, 10, 10 will be here.
Yes, sir.
So what does it mean? It means that there are two clusters, but this cluster, let's say cluster C1, is of higher cohesion. The points are very much, close to distance. So the cohesion factor or the intra-cluster average distance will be very less. Whereas in cluster C2, there is some problem, because though I am telling it as one cluster, but when I calculate the statistics of this cluster, I find that the inter-cohesion is very bad.
Yes,
so hence, I may think that this cluster I need to relook. How people relook? They just go by partitional clustering. What if there are two partitions? Immediately this partition will spread out. To detect an outlier, what you have to do? There will be one or two outliers. So you need to just partition it again once or twice. So if you have to partition it once or twice more, there is no problem with this kind of a clustering. The steps are more. That's why you lead into computational complexity and all.
Yes.
So just for the outlier detection, with the k-means algorithm and the statistics about the clusters, you can figure out whether there is an outlier or not.
Yes, sir. So another thing is there, if we consider this such type of 10, 10 very far point with respect to this cluster, then the centroid point should be go to pull to some another way.
Absolutely.
Another
After the next
then it should
iteration,
be
you will
the
see the centroid go there.
Then it should be the wrong cluster na in some cases.
No. Your cluster is not determined only by the centroid. It is also determined how the points are.
No,
I
I
mean,
am not telling
internally
like
focused.
this. No, my question is, suppose these centroids go to the far point, and then it should consider some more other points which are obviously not in, should be not in that cluster. These types of situation may be arise now.
Yes, definitely it will arise. But see, the outlier, as the name suggests, the outlier I am pointing to 1-2 points which are totally isolated than the rest.
Oh, acha.
Did you get me? See,
Yes,
what
sir.
is an outlier? It's an extreme weather among the set of weathers that you have plotted.
Yes,
So
sir.
extreme weather is a case where there are no nearby points with it. Right. So those outliers I am detecting. You are right in pointing out that if I have a multiple set of points here along with 10 cross 10, it is difficult to figure out whether this is an outlier or the whole set is an outlier. Right?
Yes, sir.
There is another subtle difficulty. Also try to think that when your centroid gets pulled in here, at the next iteration, maybe your frontier becomes only this, and this centroid makes you take these 2 points as well.
Oh, yeah. Yes,
Getting
sir.
it? Think
Yes, sir.
about this, what to do about these things, how to understand it is going bad. So therefore, in between these iterations, you need to also have a evaluation check about how good your cluster statistics is evolving. If you see that after certain iteration, though I am getting changes in the baskets, still my cluster statistics are getting poorer. That means you have lost your good points, good cluster positions.
Yes, sir.
Everybody got this part? An outlier will also try to pull the centroid towards itself. In doing so, there may be the case that earlier formed a part of the cluster may get shifted towards the outlier side, thereby relinquishing 2 points inside it towards the next cluster, which keeps on growing. That means both have now the intercohesions are poor. Intracohesions are poor in both clusters, which means in between these two in the k-means, you also have to look for the evaluation metrics of a cluster. Tomorrow's class, I will also show what is a Silhouette coefficient, which is a better measure. So we have to see that even if this keeps on changing, the number of points that you put inside a basket keeps on changing, but my cluster characteristics also is getting poorer. So I have lost a good point. So you need to just keep there. Not only stop when no number of points are changing. Right? So there is a mixture, and these are the extensions of k-means algorithms that also people try to do when it is known that I am trying to find out a scenario where my data points will be noisy or having constantly many outliers inside it. 1-2 outliers is easy to detect, but if there is a cluster of a little outliers, so there are different algorithms to do. Sometimes we follow hybrid approaches like Clara, which we will cover in the next class. Okay, that's it. So we are over time. So let me stop here. Any more questions? Then I can answer. Otherwise, yeah, sure.
Sir, can't we take median instead of mean? Then some problem will be solved, I think.
Well, if you see median, the point of saying something as a median depends on the distribution of the points, right? And mean is just the average, or it's the pure center. Median is also kind of a voting, right? It may be tilted, as you can understand.
Yes, sir. But so in that case, we don't have to deal with this outlier, because then the most dense point, our centroid will be to the most dense points.
I understand, but also see, the outlier is one of the places where you apply such kind of unsupervised learning algorithms to detect. But you also have to detect cluster it where there are no outliers as well. So I give you a set of speeches, you have to cluster hate speeches in Twitter, violent speeches in Twitter, racism speeches in Twitter, and all that. Okay, so that's why mean is just going to the centroid, and when you go for median, it has a tendency or a bias towards going up, towards voting the higher valued. So
Yes.
if you go for median, I'm Prashant, you are also right. We can go for median, but your distance metric should be very meticulously chosen.
Yes.
Right? If you give much weightage to the higher values, then the median will shift accordingly. If you do not give all as the good weightage, so you have to declare a kernel kind of a function for the distances in order to apply median into it.
Yes.
Okay. Any more? Okay. So let me stop recording and